Okay, so we're living in this incredible age where AI can generate unbelievable art, write poetry, and even code complex software. But what if I told you that these brilliant systems have a hidden weakness? A new piece of research is digging into a really common problem: why even our most advanced AIs can sometimes just completely fail at pure reasoning.
And that brings us to this fascinating puzzle, right? How can an AI write a perfect sonnet, but then get totally stumped by a logic problem that, a clever high school kid might be able to solve? It just doesn't seem to add up, but it's a thing that happens all the time.
Well, researchers actually have a name for this. They call it degenerate exploration. The best way to picture it is to imagine an AI trying to solve a maze. It finds one path that looks kind of promising, and it just commits. It goes all in, digging deeper and deeper, even when it's clearly hit a dead end. Instead of backing up and trying a totally new route, it just gets stuck. And that right there is the core of the problem.
So understanding this difference is absolutely crucial. Standard AI reasoning is really deep, but it's also incredibly narrow. It's like a train on a single track. It can go fast, but only in one direction. What this new research is all about is a shift to what's called abstraction-guided reasoning, and this is broad and strategic. So instead of that one train track, it's like having a whole map of possible routes. It's way more flexible, it's more robust, and it's much, much better at finding those clever, creative solutions.
So how do we actually fix this underthinking problem? Well, the solution they came up with is, honestly, it's kind of beautiful in its simplicity. It all comes down to the power of a good hint. The researchers introduced this brilliant idea they call reasoning abstractions. Now, you can just think of these as high-level strategies or guiding principles. To put it really simply, it's like giving the AI a cheat sheet with useful formulas, or maybe getting that one amazing hint from your teacher right before an exam.
And hey, don't just take my word for it. The researchers themselves use this exact analogy. This quote really nails it. It shows how these hints work like a key, unlocking the AI's hidden potential to solve problems that it would otherwise just give up on.
Okay, so what does one of these hints actually look like in the wild? Well, for a really complex math problem, instead of just giving the AI the question, you'd also give it a little nugget like this. Notice it's not giving away the answer at all, it's just pointing to a powerful technique, a specific way to think about the problem that makes it a whole lot easier to solve.
This all sounds great in theory, right? But how in the world do you teach an AI to not only use these hints, but to actually come up with them in the first place? Let's get into the really clever training method they developed. They created this method called RLAD, but forget the acronym. The best way to think about it is like a two-player game. You have one AI, let's call it the Strategist. Its only job is to look at a problem and come up with a few different game plans, a few of those clever hints. Then a second AI, the Solver, picks one of those hints and gives the problem a shot. And here's the cool part. If the team gets the right answer, they both get a reward. So over time, the Strategist gets really, really good at writing super useful hints.
Okay, so does this whole AI team approach actually work?
Oh yeah. The results are, well, they're pretty darn impressive.
On a notoriously difficult math competition benchmark, this RLAD method showed an average 44% improvement over other advanced training techniques. And let me tell you, in the world of AI development, getting a jump that big on a hard problem set, that is a massive deal.
And you can see it right here in the data. The basic AI model on its own, it solves about a third of the problems. Okay, if you use standard reinforcement learning, you get a little bump, which is nice, but then look at RLAD, the one using the strategic hints. It's just a huge leap in accuracy. It blows the other methods out of the water.
This research also answers a really important practical question. If you have a certain amount of computing power, what's the smartest way to use it? Should you just have the AI try to solve the problem over and over and over again, kind of hoping it gets lucky?
And the paper's answer is a clear, resounding no. It is way more efficient to spend that computing power generating a few different, diverse hints, more ideas, than it is to just generate more solutions using the same old strategy. It is literally a case of working smarter, not harder.
And right here, this is where things get kind of mind-blowing. The researchers found something they call weak to strong generalization. This means that a smaller, less powerful AI can actually generate hints that help a much bigger, more capable AI solve problems that it couldn't figure out on its own. I mean, think about that. It's like a total beginner at chess pointing out a brilliant move that a grandmaster completely missed. This is a huge deal for how we might build AI in the future.
So,
What's the big takeaway from all this? What does it all mean for the future? This isn't just about getting better scores on math tests, it's about building fundamentally smarter AI.
So why does this matter so much? Well, for starters, we're creating AIs that are just flat-out better problem solvers, more flexible, more robust. It also shows us a more efficient way to make AI smarter that isn't just about throwing more computing power at it. And by encouraging different strategies, you get a wider variety of creative solutions. We're actually teaching AI to think about strategy first, not just follow a recipe.
And this leaves us with this final and really exciting thought. If we can teach an AI to think strategically about math problems, what comes next? Just imagine an AI that could propose new strategies for discovering life-saving drugs, or find more efficient engineering designs, or help scientists untangle incredibly complex climate models. What doors are going to fly open when we have an AI that can not only calculate, but can truly strategize?